In this section, we'll generate the pink noise. We'll try to understand the theory behind it, and then we'll go to Python and implement it. We will follow a very different approach this time. Earlier, we were generating signals in time domain and then transforming them into frequency domain. That's exactly what we did for white noise as well as the brown noise. In this case, we will generate the pink noise in the frequency spectrum first, and then convert it using inverse Fourier transform into time domain. So let's have a look at what we are trying to do. What we are trying to do is to generate Fourier coefficients, basically the power spectral density of the noise using this expression here. This is nothing but an amplitude multiplied by some exponential. An exponential, as you are aware, are this expression generally is cos and sine. So this amplitude must vary randomly, and it must also exhibit 1 by f power spectral density, which is typical of pink noise. As explained earlier, the beta for pink noise is 1, so the power spectral density is proportional to 1 by f. So this amplitude must exhibit that. And then we have this phase component, and this phase must also change randomly. And by then, when we have implemented this function, a multiplication of amplitude with this expression will result into Fourier coefficients in frequency domain, and we will take an inverse Fourier transform to get it to get the time series after that. So let's understand what is going on as far as this amplitude is concerned. So as I mentioned earlier, that this amplitude must exhibit 1 by f kind of characteristic. So we will, one component of it will be 1 divided by f, which is going to implement this power spectral density. And the other component is a random noise. So this n will be nothing but a normally distributed noise raised to the power 2. And how much of it is seeping into this power spectral density is decided by this number k, which is from 0 to 1. So that's how we're going to make this randomly varying amplitude in accordance with 1 by f law. And as far as the phase is concerned, we will use a uniformly distributed phase, a randomly uniformly distributed phase, which is varying between 0 to 2 pi, which will give a random nature to this entire signal. So let's switch over to Python and implement this signal. So here we are back in the Python environment, and here we are going to implement a code which is going to generate pink noise. Essentially, we are going to generate pink noise in the frequency domain using this expression. The A must follow the 1 by f law, and it has some random component associated with it. And also this k is the phase part of it, which must vary randomly between 0 and 2 pi. So I initialize my wave parameter, my sampling frequency at 44.1 kilohertz. The time duration for noise is 6 seconds, and the number of samples is 6 multiplied by 44.1 kilohertz. Then I initialize this noise coupler factor, n is equal to 3, which is basically this factor, which decides how much of random noise gets coupled to the amplitude. So coming to this part of the code, this is nothing but I'm generating a frequency axis, and I'm generating frequency between 0 to 1 hertz, which is normalized to Nyquist frequencies. And now I have to implement random amplitude A, which is 1 by f, which should be following 1 by f rule. And I've added a small component here, 0.01, to avoid 1 by 0 kind of error. Otherwise, the software will crash. And then this part is implementing a normally distributed random noise, which is getting coupled with this amplitude. Then I'm taking the rand function, which is a uniformly distributed function, and generating a number between 0 and 1 randomly using this particular code. And this number then gets multiplied with 2 pi, and that's how this random phase gets generated. And then I'm taking the amplitude and the phase part and multiplying them together using this expression. This is exactly what we are trying to implement, as I said before. And that generates our complex Fourier spectrum, limited to the Nyquist rate, which is half of the samples must be discarded. And then, so obviously this is a complex spectrum, and I just take the real part of it, and I take this spectrum here and do an inverse Fourier transform. Why I'm doing this way is that firstly I've generated the noise, pink noise in the frequency domain, and then I'm converting it to a time series using this inverse FFT. So this is what is the signal in time domain. And then since I've sacrificed the complex part of it, so this spectrum is not the true representation. So I'm going to once again take the signal, the pink noise, which is time series, and recalculate the FFT on top of it to generate the spectrum. And then I'm going to plot this noise both in time domain and in frequency domain. So This plot is about time versus the time series, the pink noise. And then I'm going to generate the frequency spectrum, which is the frequency versus the pink noise spectrum that I just generated. So let's see how it looks. So there we are. So as we can see, firstly, this is the time domain and this is the frequency domain. Here the x-axis is time and the y-axis is amplitude. As you can see that firstly, this is not a non-stationary kind of noise, unlike a random walk. So it is, the mean is constant all throughout, and also the standard deviation is constant all throughout. So the signal is quite easily handleable in comparison to random walk or the Brown noise. But looking at it this way, you will not be able to make much of a difference between the white noise and the pink noise. So we have to shift to the spectrum or the frequency domain interpretation to understand what's going on. So here we have this spectrum, and you see that the spectrum of pink noise is entirely different from white noise. Though in time domain, it looks quite similar to white noise, but in the spectrum, in the frequency domain, it's very different. And what is different is that the lower frequencies are being passed through. They have very high power component at the lower frequencies, but as the frequencies they increase, this attenuation takes place, and this noise has very low power in the higher frequency spectrum. So this sloping of the curve is more gradual in comparison to the Brown noise. Here we saw the Brown noise, which is, you can see, extremely sharp drop because it's 6 dB per decade, and here it is slightly gradual roll off. It is 3 dB per decade, and that's how this pink noise looks. The most important part is that a lot of natural phenomena they exhibit this kind of sound, and we must understand how this signal behaves statistically. Now I'm going to take this pink noise which I generated here, the time series, and I'm again going to generate the audio file from this time series and see how it sounds. So this is the code. I'm taking the pink noise samples and sending it to my sound card at 44.1 kilohertz. And let's play it. So you can, I'm not very sure if you're able to hear it on your devices clearly, but in comparison to white noise, which is hissy, this signal is having low frequency components which are powerful, but still it has midtones in comparison to the Brown noise, which had absolutely low frequencies, and that's why the sound was very humming in nature. This is having the midtones as well, so you'll find. So that's how the pink noise sounds. Now going over to blue noise, and as I said earlier, the blue noise is now much simpler to implement. We will follow the same philosophy as we did in pink noise. We're going to use the same formula and same methodology. We are going to generate the noise in the frequency domain first, and then convert it into time domain using IFT. So the major difference being that here we are using 1/f spectrum in the pink noise. This was 1/f spectrum, but now we are going to generate this f goes into the numerator, and this can, since my frequencies are very large, it's going up to almost 44.1 kilohertz, which is a very big number. I don't want these calculations to go crazy. That's the reason I've used a log function to keep them in check so that amplitude remains in control. And then I'm going to be adding some random part to this amplitude of this blue noise. And similarly, this k is the random phase as I generated earlier, which is going to vary between 0 to 2 pi. So methodology remains the same. I generate the frequency axis. I then, instead of using 1/f function, now I'm using a log function, and the frequency function has gone into the numerator instead of denominator, and to which I'm adding a random noise which is uniformly distributed, and m is deciding how much of this noise gets coupled to this particular amplitude. And then I'm generating a random phase. Again, I've used a uniform distribution here, which is generating numbers between 0 and 1, and that 0 and 1 gets 0 or 1, any number randomly in between that interval gets multiplied by 2 pi to generate a random phase. And again, I'm implementing this function, which results in the complex Fourier spectrum of blue noise. All these calculations have been done in the frequency domain, so then I pass this data in IF50 to convert them into time domain, and that's what is our blue noise. This blue noise, I'm sacrificing the complex part of it because that generates negative frequencies which cannot be played back in on the sound card. So I'm just retaining the real part of it, and once again, since I've sacrificed the complex part, so this spectrum is not the true representation, I take the FFT of this blue noise once again and generate the blue noise spectrum. And then plot both the time versus the blue noise and the frequency versus the blue noise spectrum. So here we are. Now this is the time domain signal. You can't make much out of it because it looks quite similar to pink and white noise. But when you go and have a look at its spectrum, you can see that the lower frequencies have lower power and the higher frequencies have higher power distribution. So as the frequency is increasing, the power in the signal also increases. And that's the reason why you'll find this sound of this noise very high-pitched or shrill or very hissy kind of noise. So let's play it. So this is more like a whistling kind of a sound. Before we wind up this section, let me just play all the four sound files so that you can make a difference out of these four noises that we discussed so far. So here is the white noise. And here is the high filtered version of it, which is the blue noise. And here is the pink noise. And this is the brown noise. So I'll just summarize this entire lecture in the PowerPoint slide.